NASA has confirmed it. A planet 900 light-years away is swelling to nearly twice Jupiter's width while carrying barely half its mass. WASP 121b, a world so close to its star it orbits in just 30 hours, is being cooked to over 2,500 degrees Celsius. Its atmosphere is puffing outward, iron and magnesium literally streaming into space. Astronomers now watch it bloating in real time. But what force keeps a dying planet inflated instead of collapsing? That question begins not with WASP 121b, but with an older mystery. In 1999, we caught our first exoplanet crossing its star. Called HD 209458b, it broke the rules the moment we measured it. This world carries only about 70% of Jupiter's mass, yet its radius stretches to roughly 1 1/3 times Jupiter's size. Less mass, more volume. A planet that should be modest, ballooning instead. That imbalance should not exist, because physics tells us gas giants shrink as they age. A newborn planet is hot and swollen from the violence of its formation. Over billions of years, it radiates that heat into space and contracts, settling into a tighter, denser body. Run the clock forward, and HD 209458b should be far smaller than we see it. Instead, it stays fat, refusing to cool on schedule. Scientists named the puzzle bluntly, the inflated hot Jupiter problem. To even state that problem, you first have to trust the measurement. How do you weigh the width of a world you cannot see, lost in the glare of a distant sun? The answer is the transit method. When a planet passes directly between us and its star, it blocks a sliver of that starlight. The star dims slightly, then brightens once the planet moves on. That tiny dimming is the entire trick, and the depth of the dip tells you the size. A bigger planet covers more of the star and blocks more light. The drop in brightness scales with the planet's radius squared. A Jupiter-sized world crossing a sun-like star dims it by about 1%. From that faint shadow, we reconstruct the true breadth of a planet trillions of kilometers away. 1% measured once is a curiosity, but measured thousands of times it becomes a science. That is what NASA's Kepler mission delivered. Launched in March 2009 aboard a Delta II rocket, the spacecraft carried a single 95-megapixel camera and a 1.4-meter primary mirror, the largest ever flown beyond Earth orbit at the time. From 2009 to 2018, Kepler stared at a single patch of sky in the constellations Cygnus and Lyra, watching for those rhythmic dips across 100,000 stars at once, taking a brightness reading every 30 minutes for years on end. When 2 of its 4 reaction wheels failed in 2013, engineers salvaged the mission by using the pressure of sunlight itself to steady the craft, extending its life as the repurposed K2 campaign. All told, it confirmed more than 2,600 planets before running out of fuel. It discovered thousands of transiting worlds, turning the inflated Jupiter problem from a single strange case into a population. Suddenly, astronomers had a gallery of bloated giants, all daring us to explain them. With a crowd of inflated worlds to compare, a suspect quickly stepped forward. Heat. And not gentle heat. Hot Jupiters hug their stars, whipping around in days or even hours, some orbiting closer than 1/20th of the distance between Earth and the Sun. At that range, the star is not a distant lamp. It is a furnace filling half the sky. That furnace does exactly what you would expect to a planet's face. WASP 121b endures dayside temperatures near 2,500 to 3,000 degrees Celsius. Its atmosphere glows. And when astronomers lined up the whole population, a pattern snapped into focus. Only the planets soaking in the most intense radiation showed strong inflation. The cooler ones behaved themselves. The hotter the world's equilibrium temperature, the larger its radius tended to be. That correlation felt like a solved case until someone asked the harder question. Where does the heat actually need to go? A planet's radius is not set by its warm surface. It is set by the heat trapped far below, deep in the interior, in layers hundreds of kilometers down, where pressures climb into the millions of atmospheres and hydrogen behaves less like a gas than a hot liquid metal. That is the reservoir that decides whether a gas giant stays swollen or contracts. And here, the simple story cracks. Blasting the surface with starlight warms the outer atmosphere. It can slow the rate at which the planet leaks its internal warmth into space. but it does not directly puff the deep core region where the real-size battle is fought. To keep these planets inflated, models needed extra energy deposited hundreds of kilometers beneath the clouds. Early estimates showed the shortfall was severe. To explain HD 209458b's radius, roughly 1% of the starlight striking it had to be converted and buried deep in the interior, an amount surface warming alone could never deliver. Surface heating alone left the numbers short, so the search shifted downward, hunting for a mechanism that could carry energy into the belly of the beast. The first serious candidate arrived with a beautiful piece of physics called ohmic dissipation, proposed in a landmark 2010 paper by Konstantin Batygin and David Stevenson. It starts with the extreme temperatures we already know are there. At thousands of degrees, the atmosphere ionizes. Alkali metals like sodium and potassium, cooked in that heat, shed electrons and become electrically charged. Now add the wind. Hot Jupiters host some of the fiercest weather in the galaxy, with winds that can exceed 5,000 kilometers per hour as they race from the scorching day side to the cooler night. On WASP-121b, spectral measurements have clocked gas moving at speeds a Doppler shift betrays directly, a jet stream faster than any storm Earth has ever known. These winds are no longer just moving gas. They are moving charged gas. And when charged material sweeps across the planet's magnetic field, believed on these worlds to reach several to tens of Gauss, dozens of times stronger than Earth's, it generates electric currents. Those currents are the key because currents do not travel for free. They meet resistance, and resistance turns electrical energy into heat. The currents drive downward and dissipate deep in the interior, exactly where the models were begging for extra warmth. In effect, the planet's own storms become a wiring system, siphoning wind energy and burying it as heat. It is a planet powering its own inflation. Ohmic dissipation is elegant, but science distrusts a single elegant answer, and a competitor pushed back. This rival idea starts with the star's gravity rather than its light. The nearby star does not just heat the planet, it pulls on it. Tidal forces distort the atmosphere, creating thermal tides, waves of heat and pressure that ripple through the gas. Those tides feed into an already violent circulation. The gulf between the roasted day side and the shadowed night side drives global winds on a planetary scale. Some models argue this circulation does more than move heat sideways. It mixes it downward, dragging warmth from the surface into deeper layers through sheer mechanical churning. No magnetism required, just relentless stirring. And the honest conclusion is that these mechanisms may not compete at all. Several could operate together, layered inside the same planet. With rival theories on the table, astronomers turn to the one referee that cannot be argued with, the data itself. If you plot enough planets, the truth should reveal its shape. And it did. Studies found that inflation does not creep in gradually, it switches on. Below a certain point, planets stay compact. Above roughly 1,000 Kelvin of equilibrium temperature, they begin to swell. That threshold was a fingerprint, and a landmark analysis in 2018, led by Thaddeus Komacek and Daniel Thorngren, pressed it into the record. Researchers mapped hundreds of hot Jupiters, charting radius against the irradiation each one received. They quantified something crucial. The fraction of incoming starlight that had to be recycled into the interior climbed steadily with temperature, peaking near 2% for the hottest worlds and then tapering off in the very hottest, a curve that leftover birth heat could never reproduce. The scatter of worlds fell into a clear trend, and the trend spoke plainly. The pattern strongly favored a mechanism driven by stellar radiation, not by leftover birth heat. A sharp temperature switch is exactly what you would expect if starlight, funneled through something like ohmic heating, is doing the work. Pure internal energy would not draw such a clean line. But the most damning evidence against the leftover heat idea came from a phenomenon that sounds almost impossible: reinflation. Stars do not shine at a fixed brightness forever. As they age and evolve off the main sequence, they swell and grow more luminous, pouring out more energy than in their youth. And astronomers began finding giant planets around these aging, brightening stars that appear to have inflated a second time. Systems like Kepler 91b, a puffed giant orbiting a swollen red giant star, and the population of inflated worlds around evolved subgiants cataloged by Samuel Grunblatt and colleagues in 2016 and 2017 showed radii far larger than their old age should allow. That is the detail that closes the case, because timing is everything. If inflation were simply warmth left over from formation, a planet could only shrink from birth, never swell again. Reinflation means the radius is responding to external heating in real time, tracking the star's rising output like a thermometer. The planet inflates because the light intensifies now, today, not because of something 4 billion years ago. External radiation is not just a suspect anymore. It is the confirmed driver. Which brings us back to where we started, to the most extreme specimen of all. If starlight inflates giant worlds, WASP 121b is the experiment run to its breaking point. This planet does not merely bloat. It is coming apart. Its radius stretches to nearly 1.9 times Jupiter's, a body so distended it barely holds itself together. How barely? Consider the Roche lobe, the invisible boundary marking where a planet's own gravity loses its grip and the star begins pulling material away. WASP 121b is close to filling that boundary. Its atmosphere has swollen almost to the edge of stability. And beyond that edge, the process becomes irreversible. Gas streams off the puffed outer layers and is lost to space, bleeding away in a slow, continuous leak. We are not guessing about this loss. The Hubble Space Telescope caught it in the act, detecting heavy metals, iron and magnesium, high in the upper atmosphere where they should never survive. The observations, published in 2019 by a team led by David Singh, used Hubble's ultraviolet spectrographs to catch these metals absorbing starlight at altitudes where the temperature exceeds even the searing dayside average. On a normal planet, those metals sink and hide in the depths. Here, the atmosphere is so inflated and so hot that they are lofted to the very top and dragged out into space. Iron, gaseous, and escaping from a world being unmade by its own sun. To read the physics behind that escape, astronomers turn to a sharper eye. The James Webb Space Telescope, launched in December 2021, built to study exoplanet atmospheres in infrared light, the wavelengths where heat itself glows. Webb does not just confirm that these planets are hot. It dissects how the heat is arranged, layer by layer. And what it finds is exactly the runaway machinery the theories predicted. Webb has detected water vapor on hot Jupiters and traced their temperature structure from top to bottom. Observations of WASP 121b itself, released in 2024, mapped the planet as it rotated and revealed vaporized rock circulating between hemispheres, with the day-to-night winds carrying that material around the globe. Some worlds reveal glowing atmospheres and thermal inversions, layers that grow hotter with altitude instead of cooler, the signature of energy being violently pumped into the upper air. Crucially, the observations confirm intense heat penetrating deep atmospheric layers, precisely the deep deposition of energy that the inflation problem always demanded. So step back and assemble the verdict. The sharp temperature threshold points unmistakably to a radiation-powered mechanism. Among the candidates, ohmic dissipation best matches the observed relationship between radius and irradiation across the whole population. Starlight, converted through charged winds and magnetic fields into deep interior heat, is the leading engine of the inflated giant. But honesty demands a caveat, because nature rarely obeys a single rule. No one theory fully explains every inflated planet we have found. Some worlds may draw on residual internal heat. Others may owe part of their swelling to tidal effects, to the relentless gravitational kneading of a close star. The leading engine is starlight, but it does not run alone in every case. And whatever the exact recipe, inflation carries a bill that always comes due. A puffed atmosphere is a weakly bound atmosphere. The more a planet swells, the more loosely it holds its outermost gas, and the easier that gas escapes into space. Inflation and evaporation are two faces of the same process. To bloat is to begin dying. That death can be strangely beautiful. On some hot Jupiters, the escaping gas does not simply drift away. It trails behind the planet in a long, glowing stream, a comet-like tail of lost atmosphere sculpted by radiation and stellar wind. WASP 121b sits squarely on this path. Over time, it may shed a significant fraction of its gaseous envelope, the very layers that make it a giant. Follow that erosion far enough, and you reach a startling endpoint. A hot Jupiter stripped of its atmosphere is no longer a gas giant at all. Some of these worlds could shrink over vast spans of time to little more than bare rocky cores, the dense hearts left behind after the star boils away everything else. The largest, most swollen planets in the galaxy may be some of the most doomed, and that is why these bloated giants matter far beyond their own strange biographies. They are living laboratories, rare places where we can watch an atmosphere respond to extreme energy in real time and check our physics against reality. What we learn there reaches back into the deepest questions of how planets form, evolve, and die. The work is only beginning. Thousands of transiting giants still wait to be characterized, each one a fresh test of the inflation story. Future missions will measure atmospheric escape more precisely, watching worlds bleed into space and pinning down exactly how starlight tears them apart. Every inflated planet is a clue, and we have only started reading them. So return, one final time, to WASP 121b, swelling and glowing and streaming iron into the dark. The force keeping that dying planet inflated instead of collapsing is not some hidden internal fire. It is the star itself, its light-driving charged winds and magnetic currents deep into the planet's core, holding it open against gravity. The verdict, earned across 25 years and thousands of worlds, is simple. Starlight inflates, DYing giant world S. These are not eternal planets. They are giants caught in a slow, luminous unraveling, inflated by the same light that will ultimately strip them to their cores. In watching them, we are watching a chapter of planetary death written in real time. If this journey to a world 900 light-years away stirred your curiosity, consider subscribing and staying with us for the next one.